That's one carbon molecule to 4 hydrogens that it's bound to. So, since we're talking about organic chemistry, remember, as long as we have a carbon element or carbon atom that's present, then we're typically going to have a carbon molecule. So, in this figure, or this particular slide, we've got, 3 different molecules: ethane, ethene, and ethine. So one is an alkane molecular structure, the other is an alkene molecular structure, and the other is an alkene molecular structure. So if you notice the bonds that exist, we have carbons bound to hydrogen, and the only difference that we see among these molecular structures, it has to deal with the bonds that are present or the number of hydrogens that are present. And so let's look at ethane first. So you can see that you have a single bond from between carbon to another carbon atom. So remember, carbon molecule can only have, has 4 outer electrons to it that can bind with another, and each of those electrons can be shared with another atomic element. So in this instance, we're going to be binding to hydrogen. So one bond is shared between the carbon, so that leaves 3 electrons left to be shared with other atoms. And so when these electrons are open, then you have the highest affinity that that would be attracted here would be that of the hydrogen atom. So hydrogens come in and they're able to pair with the electrons of the carbon. So you have hydrogen here, hydrogen here, hydrogen here. And then the same thing happens with the remaining electrons that are open on this carbon on this carbon atom. For the ethene, we have carbon that has a double bond to it. So this double bond requires a lot more energy to break than the single bond that's here. So that makes this structure a little bit stronger in terms of the bond strength between both these 2 carbon atoms. So the carbon is double bound to carbon. So that means that 2 of the valence electrons out of the 4 that carbon has have been taken up by binding carbon to carbon twice. That leaves 2 additional valence electrons that are open for both of these carbon atoms to be filled or to attract hydrogen atoms to them. So we're able to, this particular molecule instead has fewer hydrogens than, say, the ethane. So that changes this particular structure from an alkane to an alkene. Now for the ethyne, which is an alkaline molecular formula, we have a triple bond that you can see. So 3 valence electrons have been dedicated to pair sharing between both of the carbon atoms inside this molecule. So that leaves only 1 valence electron per carbon atom that still needs to be paired with something in order to make this molecular structure more stable. And so the molecule or the atom of choice is going to be that of hydrogen. And so all 3 of these represent the 3 primary ways in which these carbon atoms can bond to each other. So we have single bonds, which we see with this ethane. We have double bonds, which we see with the ethene. And then we have triple bonds, which we see with the ethyne. Now, a covalent bond is a special type of bond in which you have a pair of electrons that are shared. Okay, so when we're talking about a covalent bond, we're simply talking about electrons being shared between atomic molecules. So here, take for instance these hydrogen molecules. Each of them only have 1 hydrogen bond that can be shared between with another atom. So you could have a covalent bond like you see here, with you have carbon to carbon or carbon to hydrogen. But in this figure, we just have hydrogen to hydrogen. And that just means that you have both electrons that meet each other and that they're being shared. Now, whenever we have atoms of other elements that are present and available, they can establish a bond with the carbon molecule. We refer to these as compounds. So all of these structures here that I just showed you, the ethane, ethene, ethyne, these are all referred to as molecular compounds, okay? The individual chemical elements are referred to as atoms. So hydrogen atom and carbon atom make up this ethene structure, but the entire structure, because you have multiple chemical elements in this structure, is going to be referred to as a compound. And we have some examples here outlined in this table for you, where we have the elements that are present, hydrogen, oxygen, nitrogen, carbon, phosphorus. Some of the key ones I mentioned are outlined from the periodic table. And then the number of bonds which these are able to have. So here's a hydrogen, and it has one electron available for bonding. And so you can have a water molecule or a water compound that can be formed, which is one oxygen, which typically oxygen has 6 valence electrons to it. So each valence electron out of the 6 is paired, but you have 2 open ones. So those 2 open ones can be shared between these hydrogens that fix on the side. For carbon dioxide, this is where oxygen has 2 number of bonds that are open. So oxygen can bind to carbon twice, and then oxygen binds to carbon twice again, giving the rise to the molecular compound known as carbon dioxide, which is a waste product that we ourselves generate after undergoing cell respiration. Now, nitrogen contains 3 bonds that it can produce, which means it has an affinity to bind with, it can bind with 3 different atoms. So here you have a nitrogen that's bound to 3 hydrogen, which creates the chemical compound known as ammonia. And ammonia is something that's generated whenever you have the breakdown of proteins. So when proteins are broken down, they release NH3. That's 1 nitrogen per that is shared with 3 hydrogen atoms. And the NH3, which is ammonia, can essentially cause the pH level of a system to increase significantly, making it much more basic. Which is what happens when you break down proteins. You released a lot of NH3 molecules. Here's carbon again. We've already talked about carbon. Carbon in its simplest form, when it has 4 hydrogens saturated to it, we have a molecular compound that's generated that's called methane. And this particular 4 carbon binding to 4 hydrogen is a very simple structure. So this is CH4, which would be methane. And then we also have phosphorus as an example, which contains 5 valence electrons on its outer shell that can establish 5 bonds between it and other chemical elements. So here you have phosphoric acid being produced. We have phosphoric acid being produced because we have phosphorus that's double bound to an O, and then these are also bound to OH groups. So one of the trademark of an acid is that you have 2 oxygens and a hydrogen, kind of signature tail. You can see the 2 oxygens here and then a hydrogen being formed. So that's what is referred to as an acid. So here's an example of a very complex or large structure molecule of a carbon compound. And essentially, this is kind of how carbon atoms are bonded together, and then they are either saturated or unsaturated with hydrogens. When they're saturated, they're a lot more stable. When they're unsaturated, you have stronger bonds that exist between some of the carbon atoms. And these bonds can be pretty much anywhere in this chain. And this chain, we have it at it looks like the 8th carbon molecule, where you have a double bond between these 2, carbon molecule 8 or carbon atom 8 and carbon atom 9. So let's look at the saturated molecule. This is a fatty acid structure, and we know it's a fatty acid structure because, like I said, we see double bond to oxygen on our primary element, which makes up this chain, which is the carbon, like we saw in the phosphorus, that phosphorus double bond to O. So we have carbon double bond, double bound to oxygen, and then single bound to an OH group. So this is a signature tail that indicates that you have a fatty acid. Now we know this is we know it's a fatty acid carbon, because it has the signature tail to it, but then we also have this long chain, which is a very complex molecule. So this is very similar to what a starch molecule would look like, and a starch molecule is essentially a polysaccharide where you just simply have a lot of carbons all bound to each other and then completely saturated with hydrogens being present. Okay, you have the same thing with this unsaturated fatty acid, which is down here. For this particular structure, and the primary difference is that some of the hydrogens are missing. So in this structure, we are missing 2 hydrogens. So you're 2 hydrogens short when you compare it to the saturated fatty acid. And because those hydrogens have been lost, that opens up the share pair bond between these 2 carbon atoms, which makes this particular bond strength a lot stronger than the single bond. So if we wanted to break apart this particular biomolecule, you would need to apply a lot more energy to destroy this double bond pair than you would if you had to destroy the single pair that exists. But essentially this is just, kind of an example of what a chain of carbons are. And you typically see this pattern when you have very complex polysaccharides such as starches. So when you have hydrogen atoms that are the only molecules or only atoms that are bound to carbons, we refer to these as hydrocarbons. And so a hydrocarbon is essentially an organic molecule that will only contain these 2 particular elements, both the carbon and the hydrogen. And here again is that structure of the methane, the ethylene, and then here's an acetylene, which is used inside of different our cell respiration cycle. But notice how these structures, when we look at them, this methane is very, very stable. This ethylene is a little bit more kind of conformed and maybe less stable, but it's going to require a lot more energy to break apart these double bonds between these carbons. And then one of the reasons we want to break apart these bonds, at least, when we intake an influx of biomolecules into our body, is because we want to release the energy between these bonds so that way we can generate energy for ourselves. Kind of like when you bite into a candy bar. We always talk about how we want ATP to be generated by ourselves, but that process is only made possible when we have the breaking of bonds to release energy. And then this acetylene also, like I said before, also helps in the process of cell respiration. So these are just some examples of hydrocarbons that we are exposed to or play a role in our cell molecular systems. So when we have carbon atoms that join together to kind of close a chain, which means we don't have it open. So right now this is a very linear structure of a carbon molecule. So it's just, it's not cyclic. But this carbon structure, and you hopefully remember this from Anatomy, Physiology 1 and 2, because I know some of your work that you've done in there outlines these very well. But this is, a very flat linear structure. The structure that's most common in nature is the cyclic structure. So the number of carbons are probably exactly the same. So here we've got 6 carbons, But in this structure, we have 6 carbons. Their placement in the molecular structure is different. So it's kind of like you have all the same Lego pieces, oxygen, hydrogens, and then these bonding portions that hold them together. But in here, you have the same pieces, you're just stacking them differently. So that's all that means when we talk about cyclic compounds.